Hello, everyone. My name is John McIntosh. It's my second time at 44Con. I got to speak here last year on a patch shifting tool called GDrift. And this year, I'm here to talk to you about reverse engineering Patch Tuesday. And I want to thank 44Con again for having me. I love the conference. It's been a lot of fun, and again, appreciate the chance to come and speak. So a quick who am I? You'll find me at social media at ClearBlueJar. I'm a security researcher at ClearSec Labs. I do some writing, some speaking, and mostly looking in. Most of my days are spent like head down into Ghidra and things like that. About 3 years ago now, I wrote a tutorial called CVE North Stars, and I'll explain that here in the talk. But it kind of set me down this path of doing a lot of patch shifting, a lot of reverse engineering, and that tutorial, CVE North Stars, was the idea of looking at CVEs to point you towards buggy code. So the gist of the talk, what you're going to hear from me today is that every month on Patch Tuesday, the MSRC has published all their updates. They're going to release a new update for your system. It's a large organization for Microsoft. They're handling all of the security reports that come in, and they're publishing, again, the CVEs for that. From this article here, it says they've triaged over 70,000 cases for this coordinated vulnerability disclosure. And they've issued more than 7,600 CVEs over the past, I think, well, the history kind of goes back about 20 years or so. And so every month they publish this security update guide, and it looks kind of like this. You can't really see that from where you are, but it's a long list of CVEs. And there's quite a few of them. Last month, in August, they published 119 CVEs. So we're trying to keep track of all those. It's kind of difficult to understand all the changes that have happened each month. And if you dive into one of those CVEs, they have information available to you with that. And this is an example here. It says Windows libarchive remote code execution. They have like a severity rating at the bottom. They give you a little bit more details. You can dig in, and they give you some high-level details about how serious this is. You can go and see, the attack vector was local. Its attack complexity was low. It compromises the holy trinity of the CIA, the confidentiality, integrity, and availability. Those are always high for a CVE to actually get marked as a CVE. And so there's some more information for each of the CVEs that are listed, but there's a lot of information there. They do give you some useful information to, like this last sentence here, it says, authenticated attacker with guest privileges must send the victim this file for this to be effective. And so they do give you some information about it, but the question I want to answer is, what was actually fixed? What changes were actually done to the binary? Which binaries actually were updated? A single CVE can have more than one binary that's been updated. Which ones were actually changed? Sometimes it is clear. The CVE itself will actually tell you what the binary is. In this case, they have a http.sys. That's the actual file that was updated, and that's the question I want to answer generally. But most of the time, they're not going to give you that information directly. So for all of these CVEs here, you have Win32K, which will kind of give you a scope of where the binary could be, but it's not giving you any more detail there. It might say the Windows kernel, so there's an elevation of privilege in the Windows kernel somewhere, but you don't know exactly where. And maybe that information is not useful to you, but as a security researcher or someone who wants to know exactly what has changed, you want to dig a little bit deeper. So of all those CVEs that are there, how do we tell which ones are updated, which ones are critical, which ones are likely? How do we get that information out? I don't mean to say that Microsoft is not forward-leaning and giving us information about the security updates that it does provide. Of all the vendors out there, I think they do a great job of providing us information. But I want to go a little bit deeper. I want to take your picture here. You've got this picture of Patch Tuesday. Generally, it kind of looks like this. You can't really see what's going on. You can gain some clarity by looking at external sources. And if you look at a CVE blog, you'll get a lot more information about the CVE itself. It'll dive into the details of what was fixed. I've published some things for Patch Tuesday of let's dive into the CVE, let's see what happened. You can get some GitHub POCs out there that are really useful, really powerful. ZDI itself publishes like a monthly review to say here's the things that happened during this Patch Tuesday. It includes Microsoft and Adobe, and they give you a high-level view of here are all the changes. But again, the picture is still a little bit grainy. It's a little bit more clear than it was just from the list, but you can't really see exactly what's going on. But so the whole point of this talk is, what if you wanted to go, not rely on other sources, but see for ourselves, to go and seek and find what I call binary truth, and to get this picture like this, to have this clear picture, this is what's happened, this is what's changed, and the whole talk is this journey from this blurry picture of Patch Tuesday, what has changed, what has been updated, to this clear picture. And so we're going to talk about that together. So again, here's our overview. That was the gist of the talk. Let's get into some of the history of Patch Tuesday. I'm going to show you the power of patch diffing, what you can do with diffing itself. I'm going to tell you how I reverse engineered Patch Tuesday, and basically how I provide some clarity into what those changes are. And we'll talk about the application of something I call a binography. And so we'll get into all that. So let's start with Patch Tuesday. I assume everyone in this room is familiar with Patch Tuesday. But if not, Patch Tuesday is just the phrase that we use to describe when Microsoft and several other companies release software patches on a regular basis. It always happens on the Tuesday, on the second Tuesday of every month at 10 a.m. Pacific. And actually, someone out there has built a Patch Tuesday countdown website, which you can anticipate it coming. I'm watching this at home with my popcorn, but no, it's just when they do it, and it makes it standardized. And there's a reason for that. And why Tuesday? So this is from an article I picked up. It says they give you Monday, if you're an IT guy, they give you Monday to kind of take care of anything that was happening last week. They deliver the update to you on Tuesday, and then you have time to deploy the patches as needed. And what they're trying to avoid is, all the things that we've recently seen, and with the big CrowdStrike issue that kind of came up. And that was a big thing that kind of came out. That's the idea of not deploying on Friday. Tuesday's a better day. I think Microsoft does that well. So the updates themselves, they include updates for the OS, for Office, for Visual Studio, for all of their software. They're publishing regularly the security updates on this day. It helps the updates themselves keep your software secure, up to date. Also, they add new features. So besides security updates, they can also add new features. And so they publish each one of these. They mark them with these knowledge base articles. You can kind of go see for Windows 11 and go through the history of all the updates that are out there. There's unique links for all of them. This information becomes important for later when I describe how I've automated the mapping CV binaries. Sometimes they publish KB articles that are out-of-band updates, so they can't wait for Patch Tuesday. Something's too critical, they'll do an out-of-band update. And so that's just some more history there. But if you look back, Patch Tuesday has been happening for 21 years, actually. 2003 is when it first came out. So it's been a long time. Microsoft has been in business. There's a quote here with over 1.4 billion devices each month and billions served. In the US, in McDonald's, they always have on the sign it says billions served. Well, the same thing's going on for Patch Tuesday. There's a lot of updates being distributed and passed around. So again, Patch Tuesday was introduced way back in 2003. Here is a clip from a CNET article describing how Microsoft is going to detail a new security plan. This is back in 2003, and it's talking about here are all the reasons that Microsoft wants to standardize Patch Tuesday, and here were the key reasons. One was a response to the chaos of the patch scene in the early 2000s. Essentially, Microsoft would release a patch when it was available, not on a regular basis, and so that was difficult for IT staff. There was something called the blaster worm back in 2003, and this was a RPC decom vulnerability that was wormable, meaning it could spread by itself, and it was affecting a lot of machines. This is back before the days of not everything was behind a NAT, everything was maybe publicly addressable, and these worms were a big threat. And there was something called the Trustworthy Computing Initiative, and this is Bill Gates' email, or there's a record of Bill Gates' email talking about this. And really about the idea of, computers are going to become we're going to depend on them as much as we depend on utilities. As we depend on electricity and water, we want to be able to trust our computers to provide service. And that's true even more today. And there's been several editions of this Trustworthy Computing Initiative. So The more details on this is there used to be these ship-when-ready updates that were hard for IT pros. The MS Blaster worm was the other reason. There's many names for that. Here's a screenshot of a hex dump of what that was. There was a little note for Bill Gates in there. Why you make this possible, stop making money and fix your software. This is kind of a fun, or a funny, probably not funny at the time, but today, looking back, it's pretty funny. This is what you would see when that blaster worm was going out. I was at university back in 2003, my first year, and I had an IT job, and I would go around to staff computers, and I would see this pop up. And I would try to re-image the machine and after I re-imaged the machine, before I would install the update, I would see this again. And this was the blaster worm kind of spreading itself throughout our university network at the time. So it was a big deal. And this is just more history of that. But Microsoft, Patch Tuesday, the history is that they wanted to prevent these things from spreading so fast. They wanted to make this a regular thing. So Patch Tuesday was I guess, pushed forward by this blaster worm that came out, affecting a lot of computers. Actually becomes a big part of the Patch Tuesday history. This TCI, again, this is Bill Gates saying, hey, we got to make sure that computers are secure and trustworthy. And those are the three main reasons why Patch Tuesday came about back in 2003. So what did it look like, or what did it come from, and where is it today? And that's where we're going to kind of go through. They used to not publish updates, and they used to not be forced to update. They had these things called security bulletins, and they're really just, I feel like looking back at these, and these are all published here and available, they were more like suggestions. Here's a clip from one of the security bulletins. It's like, here's what Microsoft is doing, and here's what we think you should do. It's like suggesting that you update your machine, and it wasn't mandatory. Again, you can go back and see all these security bulletins. They published them all the way up until 2017, when they switched over to the more modern security update that we'll see here in a second. But again, you can go look back at these things, and they're just telling you, like, here's what Microsoft is doing. We've discovered this security vulnerability, and we think you should go and download this patch. And it was a manual process. You had to go and download the patch yourself, apply it. Sometimes they would give you a list of the files that were affected, and it was all a very manual thing, kind of going forward. Here you could go and you'd have to actually go and find the patch yourself. And this is actually the update for the blaster worm that came out from a while back. As they realized that was kind of a tedious process, they switched over to service packs, and they switched over to something more like a cumulative update. So here, instead of giving you one patch at a time, they say, here's a bunch of patches, apply them. And so service packs is where they went to after the manual tasking. Eventually went to Windows Update. And you can go read about Windows Update in history on Wikipedia. I won't get into the full details of that, but the high-level summary is, for a decade, you had to use Internet Explorer to go download your updates. In Vista, there was a Windows Update agent that came about that started to automate some of that process. And then in Windows 10 and 11 now today now the updates are actually mandatory. It's written into the license, unless you're disconnected from the internet or I guess you never update your machine. But that's just kind of the progression for Windows Update. And really, it's a very complex thing that Microsoft is trying to solve. They have so much software out there. All these CVEs are coming in. This is a clip from one of their PDFs describing the response. And a vulnerability comes in. They have to triage it, deploy it, test it, and on the last column there, you can see what they provide to you. They provide to you the update on Patch Tuesday. They update the security guide, so all the information that you can kind of glean from those articles I showed you. And sometimes they write blogs, kind of giving you more details about the current state of security. So the MSRC security guides, we're going to focus a little bit today, because from this security guide is how we're going to kind of reverse engineer Patch Tuesday. It provides CVE details, just like the security bulletins did back then. They have some frequently asked questions, and if you're going to start reverse engineering Microsoft CVEs, start with the security guide. The CVE will be there, some extra information. So one more thing they did recently, and this is in the midst of me doing this reverse engineering, is that they started to introduce the CWE that relates to the CVE. They didn't publish this before, and they backdated it back to 2023. The CWE is the like common weakness enumeration. The CVE is like identifies the vulnerability, and the CWE tells you maybe what's the root cause of the vulnerability or the weakness. You can see I highlighted here with this CVE. They added this information, and now it becomes a little bit even more fun when you try to go reverse engineer a CVE, because you kind of have a correlation, like, oh, this is a time of check, time of use vulnerability. How can I go find that? And so we'll look into that. Again, trying to say that Microsoft gives us a lot of information, and that's why we can actually dig in a lot to this. But I will say that there's still this mystery, and this is the problem that we're going to solve. You know, what was actually fixed, which binaries were updated for a particular CVE, and those are the things I want to solve. There is an exception. Certain companies provide security software, and they get to be members of this Microsoft Active Protections Program, and I've not seen these things. That would be very useful, but they get extra information about the security vulnerabilities before Patch Tuesday comes out, and I guess my talk is a way to do this without being a member of this secret society. All right, so some don't have to guess about Patch Tuesday. So that was kind of a convoluted way to tell about the history of Patch Tuesday as a whole, but now I want to talk to you about the power of patch shifting. Now, what is the secret ingredient? The power of patch shifting? Well, it's not secret. It's just reverse engineering. It's just really a method. It kind of gives you a method to do it, a way to do it, and you're leveraging the two superpowers I'm going to call out here. The first power is the power of diffing. Focusing on just the changes, ignoring everything that's the same, and scoping the problem. You know, if you're looking at a piece of software and it's hundreds of libraries or whichever, but all you have to go do is look at the one thing that's changed, that makes it a lot simpler of a problem. So the scope of the problem goes way down. And the power of reverse engineering is kind of the ability to observe, infer, reason, and understand about what is going on. And that comes with experience, but a CVE kind of makes a great reverse engineering weekend project. To start with something that's a known problem, scope it way down, and try to go and reverse it. Again, I'm leveraging patch shifting to go and see this binary truth. I'm proclaiming, what has changed. So let's prove it. If we look at this CVE, this was a CVE in the kernel from January, and all the information that we have is, it's a Windows kernel elevation of privilege. Well, the kernel is a pretty large binary. It's about 11 megs on your machine. And if you pull that into Ghidra or your favorite SRE tooling, you'll see about 30,000 functions. But if you diff two binaries and just diff the changes over 2 release cycles, that might go down to 50 functions that you have to look at. So instead of 30,000 functions, you go down to 50, and sometimes it goes down to just 1 or 2 functions. So here is the output for the January CVE in the kernel. The table of contents there, this is the output from my tool called Ghidra, and if you zoom way in, nothing was deleted, no functions were added, only 2 functions were modified. And of those 2 functions, and a few functions were also modified, as in there were some more references to those functions. And there's RTL, UL, long multiply, and long add, which I'll get to here in a second. So the power of reverse engineering is to go and look at the code changes. So this is the decompiled output from Ghidra. And you can see at the top, maybe it's hard to see from where you are, but there's a allocation function with a bunch of complicated multiplications and additions of some integer, replaced with, and let's see the next picture, replaced with some functions that are doing some multiplication and adding, I'm assuming in a safe way. So I can look at the call diff from Ghidra. I can say, oh, this function, they added a feature flag, which is a common thing they do for a new patch. And a feature flag is a way to turn on and off a patch dynamically, or to test out the patch before it becomes unstable. But there's two new functions added. Oh, they added this ulong add and this ulong multiply function. So if we look at the old one, we see complicated multiplication and addition, and all these parameters passed into an allocation function. And in the new one, we have all of these maybe more safe ways of adding these parameters together. And at the very bottom, hard to see maybe where you are, but the allocation function is still there, but much simpler numbers being used. And so the assumption from our start to reverse engineering, looking at the kernel from 50,000 functions down to 1 or 2 functions, in this case 1 function that has changed, they've added some functions to safely calculate the integer. Another question you might want to ask is, how can you reach this function? And in this case, we can use a call graph. Again, you can't probably see that from where you are, but if you zoom in, you can say, oh, how could I actually get to this vulnerable function? Is this something maybe that an attacker could approach? Is this something that a user, or is this remote or local? You start to answer these questions when you start to do reverse engineering of the CVE. And the power of diffing is all those things that give you the ability to do that. So with reverse engineering, begin to understand the root cause and how it might be triggered. Let's look at another example. This was a recent Windows TCP/IP RCE. This was, I guess, yeah, a capability that was for unauthenticated. A series of packets could be sent to trigger this vulnerability, and it had a high CVSS score. What was fixed? Is it critical? There was a lot of CVE hype, which I'll call the CVE hype, around this one recently. Here's a random post. This is someone saying, hey guys, watch out. There's a new CVE for the TCP/IP stack. It's wormable. So, and is that true? How do we know that? And I will say people love to post CVE hype, and I don't know if I do that. This is me posting CVE hype, but this is actually me reverse engineering. At least posting the diff. I was able to post the diff, identified the function that had changed, had to do with IPv6. Looking at the side-by-side diff, you could say, oh, they're no longer calling this IP send error function. Again, I don't know much about the TCP/IP stack until you start to dig in, but all of a sudden I know where to go look. I know where to go and see for myself, and we have a starting point for reverse engineering. And then you can start your dynamic analysis. With this particular CVE, as far as I got was able to break on the TCP/IP stack, and I used Scapy with Python, and then I used, I think it was Copilot to generate me the correct IPv6 packet. I was able to get the call to happen at least, but I never finished reverse engineering because I think in that same week people were starting to post something called CVE Truth, and they had some really good articles on like how does the CVE work. That both on Twitter and on GitHub POCs. And the GitHub POC actually was a working POC that would blue screen your box, at least cause it a denial of service. And so people are leveraging diffing to dig into these, and it really is a fun way to go about it. So is this new? And the absolute answer is no, it is not. Reverse engineering is not new. I just started doing it about 3 or 4 years ago. But I did find something interesting during my research for this talk, actually, digging back into Patch Tuesday and the history of it. What if I told you that Patch Tuesday actually was born of a patch diff? And that actually becomes the history of the MS Blaster worm. And I'm going to call it the seed of Patch Tuesday. And it's just one of them, one of the reasons Patch Tuesday came about, but let's dig into this a little bit. So if you go back and look to, according to core papers, the original Blaster was created after a Chinese hacking collective called Xfocus reverse engineered the original Microsoft patch. And so Microsoft had a patch for this critical vulnerability. This was in DCOM, distributed COM at the time. And then shortly after that, Microsoft had discovered a worm that was circulating. And a worm, again, these are less prevalent now because we don't have everything exposed on the internet as they did back in 2003. But the worm was pretty serious. So the worm came from this patch, MS-03-026 was a security bulletin that came out at the time. Here's the actually screenshot from the security bulletin itself. It was telling you what the vulnerability was. It was a buffer overrun in RPC. It didn't tell you which binaries it affected, but it said, hey, this is pretty serious. You should run this patch. There was a Polish security group at the time who's credited for finding this and reporting this to Microsoft. They posted they said that they have proof of concept codes, so not POCs, these are POCCs. And then, we've proven out this is a serious vulnerability, but they just said, hey, because this is so serious, we're not going to release any of this information. And so this article here came out the same day as that the patch was released by Microsoft. But again, they said, we're not going to disclose any information. And this was like an early example of coordinated vulnerability disclosure before that term even existed. And so 9 days later, though, after the Microsoft patch and after the LSD group had posted their notification, the Xfocus group went and reversed engineered the patch. They said they read the code day after night, and they figured it out, and they posted it on the internet. So their Xfocus team here is from the internet, and they were for the internet, and they posted this patch. I think, yeah, this was 9 days later. And this is an example of uncoordinated vulnerability disclosure. And so what was the result of that? 17 days later from their publication, the MS Blaster original version appears, or at least has been recognized and it's been identified on the internet. And so this is someone's saying, hey, how critical this was, how many machines this affected. I'm not sure if anyone was at university at the time like I was, but those university networks were definitely being hit by the Blaster worm, and those RPCSS servers were falling over like crazy. So here we are today, 7,704 days later, and I wanted to go back and see, okay, well, how did they do their patch diff 20 years ago? What did that look like? I do a lot of patch diffing today. How did they do it? So let's try that together. If you want to know, like if you're going to do a patch diff, you do need certain requirements. You need a copy of the old binary that's vulnerable. You need a copy of the new binary that's patched, and you need some type of SRE tooling, and symbols help if you have them. So again, how do we get 21-year-old binaries? Well, we go back, we find an old copy of XP, we install it. You find the old security patch that was still available, at least a reference to it was still available here. This is the download link. And I went to the Internet Archive, and they actually did not have it for me, but the miracle of the internet is that someone always has the old binary that you want. And so I found this random website, it had it. And basically the question I want to answer is, which binaries were updated for this particular patch? And so a quick look, if you just do the hex dump of the binary and you grep on DLL, and we know that it's a DCOM vulnerability in RPC somewhere, you can kind of see some RPC strings in here. There's like an RPCRT4, an OLE, and so you're like, oh, these are probably the binaries that have been updated. But I went ahead and I installed the patch on my base version of Windows XP that I just freshly installed. And I saw this in a registry key called pending file rename operations. If you have critical like system files on Windows, you can't just replace them while the system is running. There's this feature with Windows to say, hey, on the next reboot, replace these binaries. And so that was what they did. They set up these pending file name rename operations. You can see 3 files there, OLE32, RPCRT4, and RPCSS. And these other temporary files, set9, set-A. So as a result of this, I could see after the restart, the binaries were updated. And then I had a list of all the binaries that had changed. And so now I have all the requirements I need to do the patch diff itself. I did mine in Ghidra with version tracking this time. And you can't see that there. But leveraging the report, the actual exploit that was published by the Xfocus group, you can see that was a buffer overflow, and you're seeing the length here was only 20 hex. More details in the buffer overflow itself is that they were using a machine name. If you look at the UNC path there, the server name / C or $C long string, they were storing that long path into a machine name which was only 32 bytes long. And so that was an issue. And this is back in the days before they had all the security mitigations they have now, probably even before DEP, but before ASLR, before all the modern things that we have today. So imagine that. And so this is actually from the write-up itself. They're telling you, what the issue was with the buffer overflow. But today in Ghidra, I could go and find that in the old binary, the same issue that they found. And then if you do the diff, you can see how they fixed it. They fixed it by increasing the string length to actually be the size that it needed to be. So patch diffing is not new. They were doing this back in 2003. All these things are the case. This is more details of the actual function where the override occurs, and there's something called get machine name. It's able to find that in Ghidra. But today we can actually use the decompile view, which I assume they did not have. And it's much easier to actually see kind of where the overwrite occurs. So again, a patch diff of the RPC vulnerability led to the Blaster worm. The MS Blaster worm is one of the main catalysts for patch Tuesday becoming a reality because of the impact. And so you have this question, did a patch diff start Patch Tuesday, or because they released the patch? I don't know. I have this idea of inception of this Patch Tuesday history and MS Blaster being a part of that. But again, nothing is new. They were different patches back in 2003, and we're doing this still today. So it's just really a powerful reverse engineering technique. I recommend it. It is fun, for this evening. If you just want to go find a random CVE, I recommend it. But it does beg the question, is there such thing as a private vulnerability disclosure? And is disclosure good or bad? I'm not going to answer that question here, but I'm just posing the question at least. MS Blaster came from a patch diff, and it had a big impact, and it affected a lot of machines, but there was a worse worm that came later. But because Blaster had already happened, people started to patch computers. They started to realize that, hey, I need to put my machine behind a firewall. There were certain effects of the first disclosure that saved you from the second. And so that's an open question generally. But again, this is the power of patch diffing. We're going to use patch diffing to look into what I'm calling the black box of Patch Tuesday. So let's talk about that. Let's talk about reverse engineering Patch Tuesday itself. Okay, and the issue I'm posing again is, what was updated for each CVE, and what is the binary truth behind each one? The manual high-level diff process, like if you wanted to do this without automation, you would find your CVE, you would identify the binaries maybe through experience, or maybe it's actually labeled like that one example I showed you. You download your binaries, you would do your diff, and start your analysis. That's kind of the manual way to do it, but let's see if we can automate the steps, those steps of 1 through 4, by just doing some, I call it pretend data science, but we'll get there. All right, so what is my path to stand before you today and talk about reverse engineering Patch Tuesday? I'll say it's this. It was a series of small experiments, kind of over a couple of years, that led me down this path. And here's a quick bullets list of those things. The first step I did was I was jumping into research. I wanted to understand, how do I jump into VR? How do I get started? Or how do I be effective? And for a CVE, what meets the bar of a CVE? What is actually a security vulnerability in today's, ecosystem? And also, reverse engineering is a great practice, CVEs, but you don't always have, a POC or a blog post, and you want to go find out for yourself. So I started by teaching myself how to do this with Ghidra, and I wrote something I mentioned before, the CV North Stars. And again, it's just a tutorial I wrote for myself, and I published. This is how I learned how to do patch diffing and do it well. And it's just this idea, again, CVE is pointing you towards buggy code, and it's a good practice. So I learned several of these things. I improved my reverse engineering skills, and then I started to learn how to map a CVE, or specific CVEs at least. Like the Windows kernel, that's pretty easy, because it's just the kernel. But to identify those manually. I started to do some scripting as well. I was writing reports, like vulnerability reports for submission, and I wanted to do like a history of the CVEs for a particular topic, like maybe the Windows print spooler. So I published this small tool called CV Markdown Charts. Essentially, it would just take information from MITRE, from Microsoft, from other CVE sources, and then output some kind of mermaid JS format, or that looks maybe like this. It would start to auto-generate these reports for me. I started to understand, okay, here are the data sources that are out there. Oh, this information is pretty interesting, at least. So from the CV data, I started to gain insights. So like here's some data from Chrome that, and by data science, I mean I'm really scraping, CV sources. There's no published one for Chrome. But I started to see like, oh, there's a bunch of use after free vulnerabilities in Chrome, and started to gain some insight by looking into this. Then there was this other data source that came out. This is WinBindex, and if you're doing patch diffing, WinBindex is for you. It is a way to go and search for a particular file, and it has all of the metadata and download links that you need to go download the binaries that you need. You can imagine that we're going to use this for this process. But essentially, it solves the problem of downloading Windows binaries without having to install the full OS, like I showed you with Windows XP. We actually have download links and the downloads from Microsoft servers, and it's a pretty powerful way to go get all the Windows binaries. Last February, I did a quick talk on something I tried to do called the WinBindex Oracle. And I tried to actually brute force some download links based on some KB information. And it works only sometimes because of the way that Microsoft embeds timestamps. But I'm not going to get into that here, but it's just another step on the path to me understanding what I needed to automate Patch Tuesday. So Ghidrift was a big one. I wrote Ghidrift to do command line diffing. This is me here last year talking about it. It was fun to share. But the main point of Ghidrift is that it is command line, as in all you need is 2 binaries, and you run this on the command line, and it outputs your diff. So that really enables automation, and we'll see that here in a second. It's powered by Ghidra, and I claimed it has social diffing, and by social diffing, I just mean its output is markdown, so you can post that in a lot of places. So those are my three kind of, I guess, benefits of ghidrift. So how do we do, automated patch diffing? Well, I released something called a WinBinDiff, and essentially WinBinDiff is just an evolution of ghidrift itself. WinBinDiff is this. It's ghidrift and WinBinDex together, and it allows you to go and build something I call a binography. And so WinBinDiff will take a file name, an architecture, and a build, and kind of show you the lifetime story of a single binary, like over time. So it gives you all the patch diffs from its when it was born until its current state. And I presented that this year over at Black Hat. And again, these were some of my slides from there. Like, what if we want to see changes over time? The biography of a binary, a binary biography, or binography. That's the word that I'm going to take away from this presentation, is binographies. And it's hard to see maybe from where you are, but here's a list of some of the output. This is a summary view of all the diffs that happened over time. It includes all the functions that have been added, modified, and or deleted. And that kind of was inspiration as well for Patch Tuesday. So if we can automate diffing of a binary over time, why can't we automate Patch Tuesday? So how do we do that? So to do that, all we have to do is add one more thing. We have ghidrift, WinBinDex data, and then we have a CVE matching algorithm. And that's what I'm going to talk about next. That's how we're going to do that. So what is the algorithm? Now, this is not AI. This is not machine learning. This is me with Jupyter Notebook and some web scraping. And so we're going to talk about that. So this is me pretending to be a data scientist. I'm not. This is what I'm doing. So let's go. Let's go big picture. So every Patch Tuesday, hundreds of binaries are updated. We only have to consider the ones that have been updated. So I have a record of maybe about 16,000 Windows binaries that are out there, like by name. And we only have to look at the ones that have been updated for Patch Tuesday. Now, you saw the CVE number before. It was like 119. And some CVEs have more than one binary that have been updated, but think about that. 16,000 down to 100. And now we only have to, and then, so how do we get it down to 1 or 2? So for each CVE, we need to maybe do some data correlation from the CVE metadata to get that number down. For my algorithm, it doesn't strive for 100%. It just tries to go for good enough. Like if I give you a couple diffs that are wrong, it's going to be okay. So let's go through that. So here are all the information sources that we're going to use. We're going to use the security update guide, which is the primary source. Windows binaries themselves have a lot of information based on the name or the description. Also the history. You might always know that a certain CVE title or tag corresponds to a binary. We're going to use KB articles, and I'll show you that here in a second, and we're going to use WinBinDex, and that's how we're going to download all of our binaries. So from the CVE information, you can kind of go through the security update guide. If you take a look at the columns, it kind of gives you an idea of what type of information you can pull from the CVEs. And the main things are the description, the tags, the titles, so the FAQ sometimes, but that's the main thing. From the KB articles themselves, like here's a dump of my data I've pulled out from KB articles. Like from the top one there's 173 binaries that have been updated. Again, that's how I get my first cut from 16,000 down to 173. We just have to start correlating data sources. And this is me playing around with Jupyter Notebooks and getting some kind of consistency. And I hope to show you the kind of results of that. So I'm building a list of all the Windows binary names. I'm trying to correlate those names to the MSRC tags that have been produced for CVEs. And I try to do like over a spectrum. Like if I do a correlation of 100%, how many binaries do I get? If I do a correlation of 50%, and by correlation I mean the names themselves to the actual like binary name and/or maybe just description of the binary, and I start to get an idea of, okay, if I use 75% here in this case, I have about a one binary match across all the binaries. So maybe that's a good number. And so I started to play around with these and started to adjust this algorithm to see what I can do. I could also start to ask questions about the CVE data that I've collected. Which of these CVE tags are a bit too noisy? Like Microsoft Edge, that's actually pretty descriptive because we know which binary that is, but one of the tags is Visual Studio. It's hard to map Visual Studio to a specific binary because there's so many binaries that relate to it. So those are ones that are more difficult to match to. But I started to ask questions of, for all of these CVEs this year, how many ones can I map binaries to? I can get that information. and basically just playing this game of this correlation. I can put all these inputs in to produce a list of my, my CVE mapping. And so it can produce something that looks a lot like this. Like every row here, the CVE, the tag, the title, and here are the binaries that are related on the very last column there. They're not only related maybe by name or description, but they've also been updated. So it's all the binaries that exist down to all the binaries that have been updated, and the ones that then and the binaries then that correlate. And so there might be 3 or 4, and let's take a look at maybe what that looks like. And again, I can ask the question of how effective this is. I can map. This is all the CVEs over time. These are CVEs that I have identified updated binaries that might be related. I can't guarantee they'll be related, but they might be related. And that average there is about 67% over the course. This is data since 2016, because that's when they started publishing all of this information in the security bulletins. And so this, yeah. Oh, I do need to talk about limitations. What needs more data? I'm mostly looking at Windows operating system files. I'm not looking at Office. I'm not looking at SharePoint or all these other things, because I don't have a big index of all of these binaries to go and download easily. And that's thanks to WinBindex. And so there's some limitations here, but there is some success and what we can do. And so let's see. What can we do if we had this big listing of all the binaries that have been updated and these CVE correlations? Well, if binary binographies tell the life story of a binary, these Patch Tuesday binographies are going to tell the story of these CVEs over a Patch Tuesday. So that's kind of what I'm going to try to make exciting. This is a quick video of just the tool running, and I'm not sure how exciting the tool can be. I've added some music to it to try to make it exciting, but bear with me. I'll try to explain as well as things go. Let's see if this works. So, can you hear me? So this is the tool running. It's gathering all the CVE data from my data source. It's going out and reaching out and downloading all the binaries that match. It has to be the binaries that match have to fall in the right specs. They have to be the update themselves. As in, like the version this came out, this is patched. I have to download the right version, the old one and the new one. It's pulling all those down. And again, this is just the console output, but after all the binaries have been downloaded and I've verified that they are the ones I need to diff, I run gdiff on all of them, and it runs about 8 at a time. At the same time, it's doing the analysis, it's doing all the diffing, and it outputs this CNE binography. And that's all in Markdown, and it comes out and it looks like this. Not all the CVEs are going to have a match, but all the Windows OS files ones should. And then you have this look of, I can go and look at the CVE, I can see which files have been updated for that, which have been modified, and then you have this this Patch Tuesday binography. And this is the answer, I guess, to me reverse engineering a Patch Tuesday. I'll look in to see if I have, I have this repo out here that I'm going to publish today. This is just the past 3 months of Patch Tuesdays. July, August, and September. You can kind of go and see for yourselves. I'm going to click on that right now to see if we can get a little bit of a sample. Don't worry about that. I have it loading over here. Okay. So again, if we go through and look at, I'll just click on September. And it's a little bit hard to see in here because of the limitations of the CSS within. This is on GitHub here, and a lot of these ones actually don't. But if you scroll down to the Windows OS files, you start to see that. If you guys can see that from there, here's the Windows Remote Access Connection Manager. It's an out-of-bounds read. Here's the file that I'm saying relates to that. This is the added column, deleted column, and then there's modified. I've identified other binaries that are maybe related or maybe not be. I'm going to assume for this case, you can zoom in. Anything that starts with RES here, I'm going to say relates to this CVE. But the thing is, it was automated based on the the data I correlated. And it's not that difficult because of how much information Microsoft provides you to do this correlation. But it's still pretty cool to kind of have this overlook, or this, what does this look like across our Patch Tuesday? And obviously you have this way to go and see for yourself, here are all the changes that actually happened. And if you want to get into reverse engineering, it's a way to go to start. So that's an example of that. Let me just adjust this. OK. All right. So we have these Patch Tuesday bibliographies. They tell the story of Patch Tuesday. They provide you binary truth because they show you the exact changes. It's going to take some experience as a start reverse engineering. You can't understand all the changes right away, but you start to understand patterns as things go forward. And that's mostly it. The summary is, with the history of Patch Tuesday, you saw the power of patch diffing, kind of how it scopes a problem and makes it simple just to go start your reverse engineering. Using publicly available sources, you can go and reverse engineer Patch Tuesday just by doing some correlation. And the application here is these bibliographies. And so that's how we go from this blurry picture of what Patch Tuesday might look like to a really clear picture going forward. And I guess I'm going to open up the gap for questions.